The news cycle is full of claims that GITAI's R1 rover has passed mock moon surface tests, and that is the headline you clicked on. But the real story is not about a successful test run. It is about whether a specific mechanical design choice actually solves the mobility problems that have plagued lunar exploration for decades. Most engineering analyses stop at the headline and celebrate the achievement. By the end of this video, you will understand why this specific actuator architecture represents a fundamental shift in how we approach lunar mobility, and why it might be the only viable path forward for future South Pole missions. For decades, the standard approach to lunar rovers has been rooted in the legacy of the Apollo era. We built machines with massive, high-torque gearboxes designed to push through the hardest possible terrain. The logic was sound for a short-duration mission. If you need to move a heavy payload across a flat surface, you need brute force. You need a system that can generate enough torque to overcome the friction of regolith and the weight of the vehicle. The Apollo lunar roving vehicle and subsequent concepts like the European moon rover system followed this heavy metal paradigm. They relied on rigid suspension systems and high-torque motors that could stall if they encountered a slope too steep or a patch of soft soil too deep. The failure mode was predictable. The wheels would spin, the torque would saturate, and the rover would become immobilized. Now consider the design philosophy behind GITAI R1. It abandons the traditional high-torque, low-speed gearbox model entirely. Instead, it utilizes what is described as a human-scale actuator design. This is not a marketing term. It refers to a direct-drive, high-bandwidth approach that mimics the compliance found in biological systems. Where a legacy rover relies on a rigid frame and a powerful motor to force its way through obstacles, the R1 uses actuators that can adjust their stiffness and position in real time. This trade-off sacrifices raw torque and maximum payload capacity for agility and mechanical simplicity. The question is whether this sacrifice is worth the gain in mobility. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. The mock surface tests provide the first concrete data on this trade-off. The results suggest that the primary bottleneck for future lunar mobility is not power or autonomy, but the mechanical interface between the wheel and the surface. In simulated regolith, the R1 demonstrated the ability to navigate boulder fields and soft patches that would have stopped a traditional high-torque rover. The human-scale actuators allow for real-time compliance adjustments. When a wheel encounters an obstacle, the actuator does not just push harder. It adjusts its stance and grip, effectively finding a new point of contact without losing traction. This is a critical distinction. Rigid systems cannot achieve this because their control loops are too slow to react to the micro-variations in soil density. This design eliminates the need for complex suspension systems found in previous generations. Every bearing, linkage, and joint in a traditional suspension system is a potential failure point in the harsh thermal and vacuum environment of the moon. Thermal expansion and contraction can seize bearings. Vacuum conditions can cause lubricants to outgas and fail. By reducing the number of moving parts and relying on the compliance of the actuators themselves, the R1 design significantly reduces the mechanical complexity that has historically led to rover failures. The data implies that the industry is moving away from heavy-duty mechanical design toward biomimetic actuation. From a systems architecture perspective, this shift changes the entire mission profile. The test results validate a production trade-off where the rover sacrifices payload capacity and extreme speed for a modular, lightweight chassis. This is a calculated risk. A lighter rover requires less energy to move, which extends the operational window of the mission. It also means the rover can navigate the boulder fields of the lunar South Pole, a scenario where previous high-torque rovers have historically failed due to torque saturation. The ability to traverse this terrain is not just a bonus feature, it is a mission-critical requirement for accessing the permanently shadowed regions where water ice is believed to exist. The implications for the future of robotics are profound. The successful mock surface tests indicate that the fundamental constraint is no longer about how much force we can apply. It is about how intelligently we can apply that force. The R1's design suggests that future career opportunities in lunar robotics will increasingly require expertise in high-bandwidth control loops and compliant mechanics rather than traditional heavy-duty mechanical design. We are entering an era where the software and the control algorithms are just as important as the hardware itself. The hardware is no longer a static platform. It is a dynamic system that interacts with the environment in a continuous feedback loop. This brings us to the critical analysis of the human-scale actuator concept. While the European Moon Rover system and MDA's Cargo rover rely on traditional wheel designs tested in analog campaigns, the R1's approach treats the actuator as the primary interface with the terrain. This is a fundamental architectural shift. It moves the intelligence from the motor controller into the mechanical structure itself. The actuator does not just drive the wheel, it becomes part of the suspension, the steering, and the traction management system simultaneously. This integration is what allows the rover to adapt to the unpredictable nature of the lunar surface without the need for complex, heavy, and failure-prone mechanical linkages. The data from these tests suggests that the industry is finally addressing the root cause of past failures. For years, we tried to build rovers that were strong enough to overcome the moon. Now, we are building rovers that are smart enough to work with it. The R1's success in mock tests is not just a validation of a new robot. It is a validation of a new philosophy. It proves that a lightweight, compliant design can outperform a heavy, rigid one in the most challenging environments. This is the insight that changes the trajectory of lunar exploration. We are no longer limited by the strength of our motors. We are limited by our understanding of how to make machines that can adapt. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.